So let's look at how xv6 uses process and threads and how it does scheduling. First thing is, in xv6, of course, every process has its own address space. And we can think of that as a thread. So we have one, per process, we have one. However, for each process, we also have a kernel thread. So since it has its own thread, that means every process has its own user stack, which makes sense, but also that every process has its own kernel stack, okay? Because each of these threads has to have its own stack. In addition, we've got a scheduler thread. And there's one of those scheduler threads per CPU. So the scheduler thread is responsible for scheduling threads on that particular CPU. So, for example, if we have, let's say, 3 processes on 2 processors, then we would have a total of 3 user threads, just 1 per process. And then every process has its own kernel thread, plus we've got 2 more kernel threads, 1 for each processor. So we have a total of 5. So now let's talk about how process switching actually happens. Okay, so we'll look at it kind of like this. This will be user kernel space. And let's say we have 2 processes. We might have, for instance, shell and cat. So what will happen is we will have, let's say the shell is running. Okay, that is, we'll have a kernel thread in here. The kernel thread is going to go ahead and enters the kernel for some reason. So it enters the kernel because of a system call. It enters the kernel because, let's say, of a timer interrupt. In any case, the kernel threads themselves will explicitly yield using switch. So switch is going to have the effect of saving this thread. Switch is going to switch over to another thread, and the thread it's going to switch over to is the scheduler thread. And the scheduler thread is going to figure out which thread should I run next. And it decides, that's a scheduling issue, but let's say it decides to run the cat thread. So it's going to also call switch, and switch is going to start executing. We're basically going to be restoring this thread, and that'll cause the associated user thread to start executing as we return using iret from the kernel. Okay. So what happens is we go from a user thread to a kernel thread. How again? System call or a timer. And then the kernel thread yields. So the 2 possibilities are it yields because a timer has gone off, or yields because it's waiting for I/O. That'll cause a switch to happen. We go to the scheduler thread. The scheduler thread runs through and basically says, are there any runnable kernel threads? Okay, if there are no runnable kernel threads, it'll just keep idling through, looking. Once it finds a runnable kernel thread, then it'll switch to it. And then that will switch to its kernel thread, and then the user thread is going to start executing by doing an iret from the kernel. So we enter the kernel from either a system call or a timer interrupt. We go through this switch to thread, find a user thread, find a runnable kernel thread, switch to that thread, and then iret from that interrupt or system call back into now a different user thread. These address spaces are going to be different. So this is going to be the shell address space. This is going to be the cat address space. Of course, these 2 threads are not in the same process. xv6 has different states that a process can be in. So it can be in the running state. From the running state, it can go to runnable. So this would be when its quanta was expired. Right, so in this case, for example, it gets saved, it gets put in the big list of processes marked as runnable, but if there's another runnable, then the scheduler thread is going to call that first, and eventually get back to running this one. Another possible possibility is that a running thread can turn into sleeping. So this would be if we are waiting for I/O. So it goes to sleep waiting for I/O. From sleeping, we can come back to runnable when the I/O completes. We do have an unused state. The unused states are for processes in the process table that aren't used for anything at all, so unused processes. And then finally, we can go into a zombie state. And the zombie state can really be from if it's sleeping, and this would be if it exits. So, well, it didn't call exit, so let's say someone killed it. Or if it's runnable, it can be killed. Or if it's running also. So this could be killed, it could call exit, it could have a fault, so some sort of an exception. Could all cause it to go in the zombie state. And we'll see what it means to go in the zombie state. And then for a zombie state, for a time, it's sort of half dead, half alive, and eventually it goes into the unused state. From an unused state, when we create a new state, when we create a new process, it actually goes to the runnable state. So that's the list of states and the transitions that can occur between them. xv6 only supports one user thread for a particular process. So if a process wants to have more user threads, it has to roll its own, but the kernel isn't involved in helping in any way. Some operating systems do explicitly support multiple threads per process. That can be handy. So that way you can, for instance, have individual threads in these different states. So as far as xv6 is concerned, the whole process is either runnable or sleeping or running, let's say. But individual threads are all sharing that same state. When you have a kernel that actually has knowledge of multiple user threads, then each user thread can be in a different state. So you could have a single thread that is sleeping, waiting on some I/O, while other threads could still be runnable or running. Context switching can be hard to get right for several reasons. First, we got interrupts happening. What else do we have? We have locking. We have multi-core issues. So we have to deal with the fact that we have multiple, and then we also have process termination. We're going to deal with aspects of all of these as we talk about what happens in xv6. So we know that on a timer interrupt, xv6 is going to context switch between processes. Okay, how's that going to happen? Well, we're going to have a switch to the scheduler thread. So we know that we already saw the context structure that contains 5 registers. Okay, those are all on a stack. So in the kernel, each kernel thread has a stack associated with it, and there is this context for everything but a running thread. So these user registers are within that context. So let's go ahead and look at the scheduler. So here's the scheduler, and here's how I'd like to look at it. Let's look here at the switch statement. So, sorry, not the switch statement, the call to switch. So the call to switch basically switched out the scheduler and switched in a particular process. So that is where we left the scheduler. And when we return from that process, okay, because that thread, that kernel thread associated with the process called switch, the first thing we do is switch to the kernel virtual memory. That is, we switch to the page directory for the kernel, okay? And then that process is done, okay? We then set our current context for this CPU to show that the process is running is 0. So it's not, there's no process running. And then what do? Well, then we go ahead and have this for loop where we're running through the procedure table. So we were in the middle of running through the table. Let's say we were at index k in the table, and now all of a sudden we're going to go look at index k plus 1. So we've got this array of processes, and we are iterating through trying to find one that's runnable. Okay. So if it's not runnable, we continue. just as a side note, we could have written this, right? We could have written this as if p state equals runnable, then indented, do all these things. Instead, the way we wrote it is p state not runnable, continue. This provides what's known as a guard. It guards the rest of the code down here, so it ensures that in the rest of this code, p state is runnable. And I like writing things as guards as much as I can, where the common case code is in here. So this is the sort of happy path, sometimes called, of code. And that way it's not indented more and more and more. The guards prevent the indenting. So in any case, what do? If we get to here, we found a runnable process. And so we go through and mark that it is the current process. We switch to its page directory. We mark that it's running. And then we call switch to switch again from the schedule into that user process. So we always switch into a kernel thread associated with a process, and then that kernel thread switches back to us. And then we find a different user process to switch to. What if the process that we just returned from is the only runnable process? Well, what will happen is we'll go through this entire table, and then as you'll see, we go through this outer forever loop, and we'll come back in the table, and we'll go through until we'll get back to that same index k, and we'll find it's runnable, and we'll switch back to it. So in that particular case, where we have only a single runnable thread on this CPU, we will switch from it into our scheduler. The scheduler will find there's nothing else to run, and we'll switch back into it. It's important to note that this array of procedures, this ptable.proc, is shared among all CPUs. So we have our ptable.proc, and we have multiple scheduler threads. So multiple scheduler threads are trying to read from this table. So therefore, it's important that we have a lock. And that's what this lock is, the ptable lock. So basically what happens is that the scheduler will acquire the lock and then go ahead and go through the process table until it finds a runnable thread. And when it finds a runnable thread, it will switch to it. When it switches to it, the switch requires that the process table lock be held. And as the kernel thread associated with the user process goes back into user mode, it will release that lock. When it comes back in, it will acquire the lock again. And so that will allow the scheduler to continue to have the lock. But while we're running in user mode, we do not have the lock on this CPU, and instead some other CPU can acquire the lock and go loop through the process table. The other thing to note is that in our for loop, we are going ahead and releasing the lock and then reacquiring the lock. If we just held on to the lock the entire time, then one scheduler would be preventing other schedulers from running it. Let's say, for instance, there are no runnable processes. Then a single scheduler would just be running through the table over and over and over and over and over again, holding that lock. So it's important that it release the lock. By releasing the lock, that can allow other schedulers to go and acquire that lock. What's the scheduling policy that's used by the scheduler? Well, it's really simple, round robin. So it just goes through in order and around all runnable processes. We already discussed the fact that if there are no other runnable processes, then the thread that yielded back to the scheduler will just rerun. Keep in mind also that acquire is going to turn off interrupts, and release will re-enable interrupts. So why do we have this call to enable interrupts right here? Well, the reason is to briefly allow interrupts so that in case there's an interrupt happening on this CPU, like let's say a timer or something like that, that would or I/O completion that would cause one of the processes to go from a sleeping state to a runnable state, that'll allow that to happen. So basically, when we set interrupts, no, we set them only for a very short period of time. They're only on for the time between here into acquire when we clear the interrupts. But however, that's a few instructions. That's enough instructions such that if an interrupt has actually been asserted, that the CPU is going to see that there's an interrupt, and before it fetches the next instruction, go and execute that interrupt. So basically, from here to here, that could allow processes to go from a sleeping state to a runnable state. A kernel thread associated with a user process calls yield on a timer interrupt. What that will do is go ahead and acquire the Ptable lock. The reason it's going to acquire the Ptable lock is it's about to go back in the scheduler, and the scheduler expects to have the lock. So we may be stuck here waiting for some other thread to release the Ptable lock. But once this gets the Ptable lock, then we can go ahead and modify the state of this process to say that it's runnable, call schedule. Schedule is going to go ahead and call switch and switch into the scheduler. So this is going to take us back in the scheduler having the lock. The scheduler can go on and do a thing. Once the scheduler actually tries to run this thread again, from this thread's point of view, it's going to return from schedule. It has the lock because the scheduler has the lock, and now it will go ahead and release the lock. So schedule and scheduler are coroutines, right? We go from the scheduler. This is one thread. And then we have another thread where we have the schedule, and we go back and forth from schedule to scheduler. Schedule is just called from yield. Yield calls schedule, and then we return from yield. So each of these knows which one we're switching to and from, and the scheduler acquires the lock and then switches over to schedule. Schedule releases the lock. And then one schedule wants to go back to the scheduler, it acquires the lock, and when we get back to the scheduler releases the lock. So that's how that cooperation happens, that dance between the two of them. We have some invariants. So the invariants are the following. So if a process is running, the CPU registers hold the process's register values. And this includes the stack pointer and the page directory register. On the other hand, if a process is runnable, then what do we know? Well, we know several things. We know that the process's context holds the kernel thread variables. That is the kernel thread registers. Right? What else do we know? So this is number one. Number two, no CPU is using the processor's kernel stack. What else do we know? We know that no CPU CR3 holds the process's page directory. Okay. And finally, no CPU's proc holds the process. This is the invariant, and we're saying that this invariant can be temporarily violated while the Ptable lock is still held. But once the Ptable lock is released, this invariants have to hold. So that's why the Ptable lock is held all the way until the process is actually marked running. We've got the stack pointer and the page directory all executing correctly. Okay. And the reason we do all this is so each CPU can have the same shared understanding that they can look at the page table and understand what it means if a process is running and what it means if a process is runnable. And in particular, that means no two processes are going to try to run the same runnable process, right? because before trying to convert it from running to runnable, we're going to be breaking these invariants. And so therefore, those invariants can only be broken while the lock is held. And therefore, the first CPU to try to run a runnable process is going to have the lock held. All the rest will wait. By the time the other processes look, the process will look like it's running and no longer runnable. Is there preemptive scheduling of xv6 kernel threads? So what if we're executing in user mode and an interrupt occurs? Well, then in that case, we're going to enter the kernel thread for that process, and it will then go ahead and call schedule, which will go ahead and switch over to the scheduler thread. If, on the other hand, we're already in the kernel, so let's say, for example, we've got an interrupt while in a system call. So we're handling a system call. Okay, and let's look at that stack. So what's going to happen on the stack? Well, we're going to have a trap frame for the system call. And then we're going to have some stuff right on the stack. We're going to have basically the system call stack as it is handling the system call. And then all of a sudden we get a timer interrupt. So now we're going to get a new trap frame. So here we have a nested trap. So this is for the timer. And then in response to the timer, we're going to call yield. So we'll have a yield stack frame. Yield is going to call schedule. And then we're going to have our context. Since this is going to now be made runnable and will be in the scheduler thread, and then we'll go run some particular thread. So xv6 does allow preemptive scheduling of its kernel threads. Again, different from JOS. JOS doesn't allow timer interrupts to happen while you're in the middle of a system call. Instead, once the system call is over and we return back to user mode, then all of a sudden that timer would take us back into the kernel. There is a rule in xv6 that says when you yield a CPU, the rule is don't hold any locks except the Ptable lock when you yield a CPU. And the reason for that is otherwise someone else who is waiting for the lock may basically be holding a lock that's held by a non-running thread. So we don't want any locks to be held by anything other than the actual running thread. Again, except ptable.lock, which is sort of this funny case where we pass it across from the kernel thread for a process to the scheduler thread. Okay, so we could just have one CPU sitting there waiting a long time. And we could even have deadlock that could occur because acquire is actually running with interrupts off. And so therefore an interrupt may not occur in order to release that lock. So basically, you don't call yield until you've released all the locks except ptable.lock.